Okay, how is dV/dt? So we're going to take the derivative of this volume formula with respect to time. How is dV/dt related to dy/dt if x is constant? All right, so again, we're starting out. Let's stop this a minute. Some reason why I disconnect from my computer and then reconnect doesn't like that. All right, so v is 3x squared y. So if I want to take the derivative with respect to t of both sides, on the left, I would have dV/dt. Okay, pretty straightforward. The derivative of v with respect to t would just be dV/dt. I know my 3 is a constant, so I can just bring that out. I'm not going to take the derivative of that because of product rule, or multiplying by a constant when doing our derivative. But then it says x is also a constant, so it's x squared I'm going to bring out. Okay, so think of x as a number 5, or whatever it is, times the derivative of y with respect to t. All right, so how is dV/dt related to dy/dt if x is constant? Well, in this case, I would just write it as 3x squared. dy/dt is the only thing that could change, and so I'll have that, leave that just as dy/dt. Okay. Same problem, but now if y is constant. So again, v is 3x squared y. So dV/dt would be 3y times ddt of x squared. Yeah. Yep, so it's constant multiple rule. So remember, if we had, like, say, y equals 5x, if I wanted to find the derivative of that, well, that with respect to x, so this would be dy dx equals constant multiple, 5 just comes along, and then really all I'm doing is ddx of x, and the derivative of x with respect to x is 1, so it's 5 times 1, and so dy dx is just equal to 5. So it's constant multiple rule. We're going back to all of our derivative rules. Okay. If I have a number that's being multiplied, again, this has to be multiplied. If it was 5 plus x, that would be different. Then it would go to 0. The 5 would go to 0. But because a constant multiple, I can bring the constant out. I don't have to take the derivative of that constant. So it's going back all the way. So now with these ones saying, okay, y is constant, so I'm not going to take the derivative of y. Okay, so think of y as a constant, think y is just a number. Okay. All right, so back to this one. What is the derivative of x squared with respect to t? Jacob. So 2x, and then what? That dt. dt is on the bottom. dx dt, okay? Don't forget that. So this is chain rule. So the derivative of x squared with respect to t, I bring the 2 down, the inside stays, so that's why it's just 2 times x. And then the derivative of x with respect to t is dx dt. And I could take this one step further just to clean it up. I would say 6xy or yx, doesn't matter. dx dt would be my derivative. Yep, yep, yep. You can leave it just like the bottom. Okay. All right, same setup now, but I say, how is dv/dt related to dx dt and dy dt if neither is constant? Okay, so I have v is 3x squared y. I want to take the derivative with respect to t on both sides. But it says neither x nor y are constant. So I'd have dv dt equals 3 can come out. And so all I'm doing is d dt of x squared y. What is the derivative of x squared times y with respect to t? Answer, Jacob, or a question? Okay. Bringing them out makes it easier. It just makes it simpler to do the derivative, I feel. Okay, but no, if you left it in there, it would still work. Okay, so how do I find the derivative of x squared times y with respect to t? Jacob? Product rule. Okay. All right, so Jacob, keep going with it then. Nope. 2x. There you go. Don't forget that. Times y. Oh, sorry. Okay. Exactly. Okay, so this would be 3 times 2x dx dt times y plus x squared dy dt. And so now we could distribute through, so this would be 6xy dx dt, and then this would be plus 3x squared dy dt. All right, so implicit differentiation, that was just kind of a refresher. Implicit differentiation is key when working through these problems. So I guess 5 actual example scenario type problems we'll do. So you get to listen to me for a while today.
Are they all 3 parts like that?
What's that?
Are they all like 3 parts like that?
Harder.
Oh.
Oh, no, I didn't break them down. No, they're all on one page. I'm sorry, not harder, but more involved. I won't say harder. Okay. Here we go. Here's our ladder problem. So just like we had on that opening screen here. An 8-foot ladder is leaning against a wall. Okay, so I've already put a nice diagram on here, but I know that hypotenuse of my triangle is going to be 8. Okay. The top of the ladder is sliding down the wall at a rate of 2 feet per second. Okay. And so if I think of over here, it's sliding down the wall at a rate of 2 feet per second. So I'm going to think of x and y's because I'm on a coordinate. I mean, this is x and h. Don't worry about that. I'm just going to work in x and y's just to make it simple. So I'm going to say dy dt, because it's sliding down, is a -2. Okay, because it's moving at a rate. It's going down the y-axis, so I'm going to call that -2. Natalie, what's that? Yeah. Yep. That's why I thought about printing these off for you guys, but I guess that wasn't that nice. You had 2 weeks off. Your wrist needs to get conditioned back to being able to write. Throw us in the deep end. You got your water wings on. You're all right.
Exactly. Come on.
Okay, so ladder is sliding down the wall at a rate of 2 feet per second. So my dy dt, so they're giving me that rate, is 2 feet per second. So I'm going to write dy dt, and I'm going to say -2, label it on my diagram, that I have a rate going on in that y-axis. Yeah, it would be feet per second, but you don't have to worry about velocity, acceleration, any of that right now. How fast is the bottom of the ladder moving? Okay, and so we have movement going this way with our bottom of our ladder. I'm going to call that dx dt, and I'm going to put a question mark because we don't know that. We're trying to figure out how fast is our ladder sliding out to the left, the bottom of the ladder. So it's coming down and then it's going out at the bottom. Moving along the ground at the point when. All right. So whenever you see this, and you'll see it in every problem, at the point when, that number, hold off. That's going to come in at the end. So you're not putting that in yet. At the point when the bottom of the ladder is 4 feet from the wall. So I just make a note here and I would say X is 4. Okay. So that's kind of like that spot when it's 4 feet from the wall. We got to do all our derivative stuff before we tackle the when portion of it. Okay. So we have in this top triangle here, my hypotenuse of my ladder is 8. I'm going to label that as a variable. I'm just going to say z. So I have x, y, z. And I know this is a right triangle, so I know I'm going to use Pythagorean theorem. So I know x squared plus y squared equals z squared. This is what I'm ultimately going to take the derivative of. Okay, so that's that step 2 on that sheet that I gave you. Figure out your relationship. Are you working with right triangles? Can you use Pythagorean theorem? Are you working with triangles? Can you use a trig function? Are you working with an area problem? Are you working with a volume problem? Are you working with a similar triangle problem? It's typically going to be only one equation. Okay? So x squared plus y squared equals z squared. So we have our equation. Now let's differentiate with respect to t. What's that? Nope. Nope. Don't do anything yet. Okay. All right. So ddt of x squared plus y squared equals ddt of z squared. Because if you put the number in, Zach, when you do your derivative, well, depending on where it's at, if it was like a number plus, then you would eliminate that number from your calculations. So you don't want to do the derivative. You want to leave the derivative piece with variables. Okay, so the derivative of x squared plus y squared would be 2x dx dt plus 2y dy dt equals 2z dz dt. Okay. What is dz dt, or what does dz dt even mean? Okay. dz dt would be the rate of change of the ladder. The ladder is not changing at all. The ladder is a constant length. It doesn't matter. It's just going to stay that constant length. So that's actually 0. So this whole side here goes to 0 in this problem. Okay. So dz dt, that helped us out because that's a ladder. That's a fixed object that will not have a change. Okay, and that will stay just 0. Okay, all right. Now, after we've done the derivative, now we can start substituting in the when stuff. Okay, so 2 times x, my x is 4, dx dt is what we're trying to find, plus 2 times y. Well, do we know what y is? If this is 4 and this is 8, can I figure out what y is?
Yeah.
Okay, and so that would be our Pythagorean theorem, but in this case, it would be 8 squared minus 4 squared. So 64 minus 16, which is 48. But we're going to take the square root of that. What's the square root of 48? 4 root 3. Okay, so this becomes 4 root 3 dy dt we know is a negative 2. So now I have one equation with one unknown that will tell me what dx dt is. And so this would be negative 8 times 4. So we can work this one out. So we end up with, I'm going to move it to the other side, it'd be 16 root 3. 2 times 4 is 8. So dx dt is equal to 16 root 3 all over 8, which we could simplify to just be 2 root 3. And it's a rate. So in this one, it's feet per second. So what this is saying is when the ladder is exactly 4 feet from the wall, okay, so we stopped time for a second, it's sliding down, but at that instant when it's 4 feet from the wall, the bottom is sliding at 2 root 3 feet per second at that instant. Okay? Not bad, right?
You're making a way bigger deal out of it.
Good.
Get harder.
No, it's just the harder part is finding which equations to use. Okay, that's the hardest part, and that's not even. And that's what I felt like I was maybe overhyping it a little bit. All right, let's do another one.
Give it a 9 out of 10 on that.
A circular metal plate is heated in an oven. Its radius increases as a rate of 0.05 centimeters per minute. So as I'm reading through problems, I'm identifying key information, okay? Its radius increases at a rate of 0.05 centimeters per minute. So I'd make a note to myself, I'd say, okay, drdt, I know is 0.05. All right, when you're doing these on Math Excel, you just have to write it on your paper. You obviously won't be able to write it on the paper, problem being on a paper. So as I'm reading through it, I'm pulling out, okay, they tell me this. The radius is changing, so I'm going to say drdt is 0.05. At what rate is the plate's area increasing? So right there, I know dA dt is what they're asking me to find. At what rate is the plate's area increasing when the radius is 47 centimeters? Again, this when piece, hold off on that, okay? That's a piece of information we're going to use later on. We're not going to use it right now, but that's going to come into play later on. So they want to know with the circular metal plate that's being heated up, when the radius is actually 47 centimeters, what is the rate of the area changing on that plate? So what formula are we going to start with? A equals pi r squared. Okay. Differentiate with respect to time. So dA dt would be equal to pi is my constant. Derivative of r squared with respect to t would be 2r dr dt. This one conveniently already is set up to equal dA dt, which is what we're trying to figure out. So we have pi times 2. We have r. Now we can substitute that r in of 47 times dr dt, which we also know is 0.05. Work all this out, and I end up with 4.7 pi. What would be my units on this? Centimeters squared per minute is how much the area is changing at that exact instant when my radius is 47 centimeters. Okay, it's being heated, so it's continuing to get bigger and bigger and bigger, or the area is changing. Okay, but that exact instant, it is changing at a rate of 4.7 pi. That's not the area of the plate. The area of the plate's not 4.7 pi. That's the rate of change. That's how the area is changing. All right, that was an easy one. Come on. Uh-oh. My thing's not responding.
Uh-oh. Yeah, we're time, maybe?
There it goes. All right, let's do another one. A balloon is rising up from the ground. So again, we want to just make a quick little diagram here. So I have my balloon, and it's rising up from the ground. Give me a second to write this down. Okay, so we have our balloon, and then we have our person who is 500 feet away, and they see the balloon at an elevation angle of pi over 4. So this angle here is pi over 4. Yes. It's 500 feet. It's 500 feet. It's going to look like a dot.
Yeah, there's a dead dot.
So my balloon's a little bit off. There you go. There's my balloon. Okay. Sees the balloon at an elevation angle of pi over 4. The angle is increasing at a rate of 0.14 radians per minute. So I know d theta dt is 0.14. How fast is the balloon rising at that moment? So I'm going to call that dh dt for the height. That's what I do not know. That's what I'm trying to figure out. I'm trying to figure out dh dt for this one. Okay, so can we use Pythagorean theorem on this one? Nope. Can we use a trig function?
Yes.
Okay. Which one can we use? Tangent. So tangent of theta, if I label this side h, is going to be what? H over 500. So opposite over adjacent. Opposite my angle would be h. My adjacent is 500. Okay, but I'm trying to solve for dh dt, so I'm going to rewrite this as h equals 500 times tangent of theta. So now I already have it equaling my h. So when I take my derivative, dh dt is what I want. 500 is my constant. What is the derivative of tangent again? Secant squared. So this is secant squared of theta. D theta dt. Okay? Because we're taking the derivative of tangent of theta with respect to t. So the derivative of tangent is secant squared. Theta stays d theta dt. Now we can put in what we know. Okay, so dHdt is what we're trying to find. So 500 secant squared of theta, my theta is pi over 4. D theta dt is 0.14. What are these calculators clicking? Secant squared of pi over 4. Okay, so that's secant of pi over 4 squared. What is secant in terms of sine and cosine? 1 over cosine of pi over 4, quantity squared. What's the cosine of pi over 4? Root 2 over 2. Okay, Jacob, I think you're getting ahead of us. So this is 2 over root 2 squared, which is 4 over 2, which is 2. Okay, so this is really 500 times 2 times 0.14. Which is 140. Say it louder, is that? Feet per minute, exactly. So 140 feet per minute is how fast that balloon is rising at the instant that the angle of elevation is pi over 4 to the balloon, somewhere on the balloon. right? So here's an example of a triangle one where it wasn't Pythagorean theorem, but we could use trig functions to figure out what it is. I got two more. No, maybe, I guess. Might end up doing that.
Next one's gonna be similar triangle.
Nope, not yet. Next one's a good one. Not a good one, isn't a hard one. What is going on with the computer?
The faucet one?
Nope.
Oh.
Okay. All right, so you don't have to write this one down word for word. So don't even write, we'll set up the diagram and that'll be enough. Because if you try to write this one down word for word, I put extra stuff into this one.
Is Deputy Johnson a random name or?
Oh, that's,
Name.
yeah, it used to be Smoes and I just changed it. Okay, all right. Deputy Johnson is chasing a suspicious dark green Mustang. What year is your Mustang? I was trying to. 2000. Okay, I was close because I was trying to Google image it, and I was on like 2015. I'm like, no, it's not that one. 2010, I don't think it's that one. And then I kind of gave up. Okay. So this one's in context. South on 148. Okay, everybody knows 148 is the road the school's on. Okay, so like you're coming from Fruitport to the school, approaching 104. Okay, so he's coming down this way. The criminal makes an erratic turn east, trying to get to 196. When Deputy Johnson is 0.6 miles north of the intersection. So I'm going to just say my Y is 0.6. And the criminal is 0.8 miles east of the intersection. So 0.8. A police helicopter flies over and determines the distance between Deputy Johnson and the criminal is increasing at 20 miles per hour. So where's that going to go on my diagram? Okay. How should I label that? DZ, okay. So this is a rate. So it's increasing at a rate of 20 miles per hour. So DZDT is 20. If Deputy Johnson is moving at 60 miles per hour at the instant of measurement, okay? So dy dt, we're working on a coordinate plane here we're making. He's going closer to the origin, so this is actually a negative 60 because he's going down, if you want to think of it that way. Okay, so dy dt is negative 60. At the instant of measurement, how fast is the criminal going? dx dt is what we are trying to find. All right, so there's extra fluff built into this one, but you get the diagram from here. So again, draw a quick sketch and fill in what you know and fill in what you're trying to figure out. Okay. We have a right triangle here. How could we tackle this one? Okay, so let's go with that. X squared plus Y squared equals Z squared. So just like the first problem, 2x dx dt plus 2y dy dt would be 2z dz dt. Now that we've found the derivative, now we can start putting in stuff that we know. So 2 times my x, which is 0.8, dx dt is what I'm going to find. 2 times my y, which is 0.6, dy dt is a negative 60, equals 2 times z. What is z for this one? Jacob. It is 1. Okay. So 0.6 squared plus 0.8 squared is square root of 1, 1. Okay. So z ends up being 1. dz dt, in this case, we do have a value, it's 20. So this is not like the ladder problem where it's held constant. This one, we know that it's increasing at 20 miles per hour. So we'd leave it positive. Okay, so we have this big long equation with only one unknown, and I will tell you that dx dt ends up being 70. I think we're all good now. We can figure that, do the math for that. What would the units on this be?
Miles per hour.
That's right. Okay, so miles per hour. So he's still accelerating. Seen that? I think that green Mustang has went 70 miles an hour past my house. You have not. You are very good. So is your brother. What is your brother doing home still? When's he starting back to school? Yeah, your older brother. Oldest. Day after his birthday?
Yeah.
Okay, he must have assumed I knew his birthday. But, all right, well, good. So you got a full house again.
Alright.
And he's still at Alma, right? He's still at Alma? Okay. One more.
Similar triangle.
That's right.
Yeah.
I don't know why my thing is nuts. There we go. All right. Hunter, who is 2 meters tall, walks toward a lamppost on level ground at a rate of 0.5 meters per second. I'll let you fill this one in and then we'll go. And I'll tell you, you have one almost identical to this in your Math Excel assignment. So take good notes on this one. What?
Is it tomorrow?
Yes. And Friday, but I'll probably have a couple more related rate problems outside of Math Excel for you to do on Friday. Friday will be the fun day. And it'll only be slightly more fun than today because every day is fun here. Is your hand okay, Julia? I see you supporting it. Maybe for next year's calculus class, I'll just print these off so you guys don't have to write them all well, so they don't have to write them all down. Okay, so let's set this up as a quick little picture. So here's my lamp post. Okay, and we'll go this way, and we'll say Hunter's somewhere here in the middle. So I actually draw. Okay. So Hunter, who is 2 meters tall, so let's put a 2 next to him, walks toward a lamppost on level ground at 0.5 meters per second. All right, so I'm going to say dx dt is going to be 0.5 meters per second. The lamppost is 5 meters high. How fast is the length of his shadow decreasing when he is 3 meters from the post. So I'm going to say this x right here is 3. I'm going to divide this up a little bit, and I'm going to say this distance here is s for his shadow. Okay, so to the left of him on my diagram, that represents his shadow, but the distance from him to the lamppost is 3. Correct, as he gets closer to the lamp, because it's shining straight down on him as he gets closer, the shadow would be smaller. Okay, all right, so here's our scenario. So this is one with similar triangles. So I have this small triangle going on, and then I have a big triangle going on. The small triangle, I'll say, is what's left of him, so that's S, and that's 2. The bigger triangle is S. I'm sorry, my S's look like 5s. S plus 3, and then this is 5. Okay, so let's review triangle similarity, how we can create these ratios. So I could say S all over S. Oop, I don't want to do this 3. I made a mistake. Don't want to put that in yet. Leave it as X. I made the mistake. Not till after we take the derivative do we start putting numbers in. Unless they're constants, like 2 and 5 are constants. I'm not going to do anything different with that. So this is S plus X would be the same as 2 divided by 5. That would work. Or we could also say 2 over S is equal to 5 over S plus X. That also works. But we cannot crisscross. We cannot say 2 over S plus X equals 5 over S. That's false. So you got to keep the sides the same in your ratios. All right, let's just tackle the one here on the left. All right, so I have these two ratios, so I could rewrite this as 5S equals 2 times S plus X. So therefore, 5S would be 2S plus 2X. Subtract the 2S, end up with 3S equals 2X. Because remember, I'm trying to figure out what is ds dt. I'm trying to figure that out. Okay, so if I differentiate this, I would have 3 ds dt is going to be equal to 2 dx dt. I know dx dt is 0.5. I'm trying to solve for ds dt, so I could divide this by 3, and I end up with ds dt equals 1/3. Okay, and this one would be meters per second. Now, in context of this problem, pay attention to what they're asking. Okay, they are saying decreasing. They are saying how fast is the length of his shadow decreasing. So on like the AP test, you would say the length of his shadow is decreasing at a rate of 1/3 meters per second. Okay, I mean it should be implied because if you just wrote 1/3 meters per second, that's a positive number, and so really you're saying it's increasing. Or you could write, okay, but don't say decreasing at a rate of -1/3, because then that would be counterintuitive. Okay, so be careful on this one. And so if you wrote it out in words, I would say decreasing at a rate of decreasing at a rate of 1/3 meters per second. Or you could just say DSDT is negative 1/3 meters per second. So this one's kind of goofy on how you would explain it from, you just have to be precise on how you would justify your answer on this one. Okay, that's it. So tomorrow will be a work day. We didn't do a cone one. You'll get one in your, yep, you'll be fine.